Yeah, so yeah, you remember we proved, well, essentially proved Riemann-Roch, right? So Riemann-Roch theorem. So this was the statement that dimension of L of D minus dimension of L of K minus E equal to degree of E minus G plus 1. I think if you want to measure the level of civilizations, you can put this formula in a kind of satellite probe or something, send it to Mars or some maybe far distant civilizations. And if they understand what this means, they are civilized, otherwise they are not. So I know this thing is controversial to say such things, but I don't care. And this is being recorded, so okay. Okay, so when D is a divisor, so we apply this. Okay, so maybe I just don't go too fast. Maybe where L of D is the set of all F belonging to meromorphic functions on X, such that divisor of F plus D is bigger than equal to 0. In this case, K is a canonical divisor. I.e. the divisor of a meromorphic 1-4. Omega belonging to M1 of X. So this is the divisor of a meromorphic 1-4. And then, of course, G is the genus and all this. Okay, so I had several corollaries, but one of the corollaries that was I did in the last lecture, I mean, the last thing I did in the last lecture was the following, is that for any Riemann surface X with genus G, and then for any point P on X, we showed that there exists a holomorphic map or meromorphic function F belonging to M1 of X with just a single pole at P with a single possible pole, of course, or I mean, with a single pole, no, at P of order at most G plus 1. So to prove this, we just apply Riemann-Roch to the following divisor. We just applied Riemann-Roch to this divisor D, which is equal to G plus 1 times P, right? So we applied it to this divisor, and then we calculated everything, and this dimension came at this 2, and then it was so on. Now, you can consider this F also defining a function from your Riemann surface, a holomorphic Riemann surface, to the Riemann sphere, because meromorphic functions are exactly those maps, right? So this F basically gives us this F, which is the same thing, but we just interpret it. So we just now we interpret points at infinity as points on C hat. So it gives us this map F from X to C hat. So now this map is a ramified covering with at most G sheets, right? Did I prove at most G or G plus 1? What was the statement I proved in the last lecture?
It was G plus 1.
Was it G plus 1?
Mm-hmm.
Yeah, it's G plus 1. So the example I will give you will show that very clearly. So F from F to XL with, so it gives us a ramified covering with at most G plus 1 sheets over there. I mean, it could be less, but at least this much we get. I mean, this sheets is really just a ramification index, which is going to be also ramification index of that pole. I mean, the order of the pole. That's what it is. Okay. So that's what we did in the last lecture. It's a very general result. Now let's take G equal to 0. See what happens. Okay. So if you take G equal to question. Okay. So if you take G equal to 0, let's see what happens. So in that case, G plus 1 is 1, and then one-fold ramified cover is just really a bijection. So corollary of corollary is that for G equal to 0, we obtain that there exists, basically what we obtain is that all Riemann surfaces of genus 0 are isomorphic. Obtain that all the Riemann surfaces of genus equal to 0 are isomorphic. So isomorphic means that they are biholomorphically equivalent. So there's a biholomorphism between them, right? So i.e. biholomorphically equivalent. Morphically equivalent. Okay, so first of all, let's see the proof, and then let's see why this result is so amazing and so powerful and so strong, actually, that doesn't maybe at first one does not appreciate, but I will try to justify that. So proof, well, let G be equal to 0 in the corollary, right? I mean, so okay, so basically what I'm saying is that for any X with genus equal to 0, of course, compact. Let's not forget that. We just have compact, because otherwise genus even doesn't make sense, right? Corollary implies that there exists F from X to C hat, which is a one-fold covering, so it means that it is a bijection, which is a bijection, right? Okay, that's the end of the story. So okay, so then hence X. So we show that all compact genus 0 Riemann surfaces are biholomorphically equivalent to Riemann sphere. This is a unique one, of course, we defined it. I mean, not a unique one. It doesn't make sense. It's a very canonical object that we define. It's C hat, right? So this is Riemann sphere. Okay. So all of them are biholomorphic to Riemann sphere, so all of them are biholomorphic to each other. So there exists in genus 0 case only one complex structure on a genus 0 curve. You see, topologically, this is not a very strong result. Topologically, they knew that forever, that there is more or less one compact oriented surface of genus 0 and all these things. That was known. But holomorphically, there exists a unique structure, is quite surprised. I mean, it's quite a strong statement. So let me actually tell you maybe in one by one method why this is so strong.
Professor, you said
Yes.
by the previous corollary, you said that there is a meromorphic function that has a pool of order g plus 1 at p, right? For the corollary that you just read.
Yes,
So if g equals 0, isn't that a pool of order 1?
yes.
So how is that?
It goes to infinity.
Oh, okay. So the point is at infinity, right?
Yeah. No. I mean, you see, I said that you can. Yeah. Okay. So I know. So you see, you can think of meromorphic functions. Now you're thinking in terms of meromorphic function.
Yes.
That's why infinity bothers you.
Right.
But if you look at as maps into Riemann sphere, infinity is like any other point. So it's an order 1 means that it's unramified at that point. So it's a base is a perfectly nice
Only if it's order more than 1,
yeah.
you have to.
Then you will have like a pinching at that point. Yeah.
And
Okay.
you mentioned that if the surface is compact, genus doesn't make any sense. Why is that?
No, if it is not compact.
Yeah, right.
So you can have like maybe holes all the way up to infinity. For example, this could be genus infinity. Anyhow, so it's not the classification of non-compact Riemann surfaces. It's a totally different story. It's you're in a different ball game.
And
There is a theory, but it's very different.
so the complex plane C is also a Riemann sphere, right? But it's not. The complex plane is also a Riemann surface, right?
Yes, but it's non-compact. It's not yet.
So it's not biholomorphic to C hat, right?
Not at all. But in that case, it's not even topologically the same. They are even topologically different.
So the compactness is very important.
Very important. Very important. Big time important. But now let me convince you why this is such a surprising result. And actually, you should be really on your toes when you see this result. Let me tell you why. So imagine you have a Riemann surface like this. Like a dog bone or something. You just create, okay? So what you do, you can just take a tube and then elongate it like that, and then you create something like a dog bone on the exterior surface. So, and then you can put it in a space. This will take a metric, okay? So then there is a Riemann surface structure here. So we are going back to first lecture now. So there's a Riemann surface. And then now you can take this one, which is the picture we all have of Riemann sphere. So this is C hat, and this is X. So topologically, this is genus 0. Okay. So what the result says that there exists a map F from here to there, which is a biholomorphism. But biholomorphism means that it's a conformal map, is orientation preserved. Okay. So this map F is conformal. So I'm going back to lecture 1 now. It's good now to you check what we did in lecture 1. So conformal means is angle preserving. Right? Is angle preserving and orientable. And oriented. These are the two properties of bijective holomorphic maps. They are conformal and angle preserving. Okay, so then basically you can map this dog bone onto your sphere in such a way that the angles here are preserved angles. It's a highly non-trivial result. If you want to prove it using differential geometry, you have to solve some PDEs, which are, there's no reason you could, the solution exists, and it's a global problem. This is completely non-trivial. So there we go. This is the result of this. And we could prove, by the way, this result only using Riemann-Roch. We couldn't prove this result without Riemann-Roch. So this is really a drastic first impression that you should get. But it's such a powerful result. Of course, you can take any other shape, any other kind of things, not just dog bone, maybe some other things that your favorite things, and then you can conformally map it into Riemann sphere in a bijective manner, orientation preserving manner as well. Mm-hmm. So
let's say we take this dog bone and flip it.
Flip it.
Yeah.
In what sense?
Make it upside down.
What's that?
Make it upside down.
Okay.
Then that's still a Riemann surface. It's still compact.
Yeah.
There still exists a conformal map into the Riemann sphere.
Yeah.
So there exists a conformal map between the dog bone and the flipped dog bone.
Yeah.
It's trans.
Oh, absolutely.
Yeah.
Yeah, there is, yeah. There's any, I mean, it could be something like this. This with that also. Although, I mean, I should be careful not to jag it here. I mean, it should be smooth, okay? This is also completely holomorphic to this. Okay?
Look, I have a general question.
Yeah.
When we define Riemann surfaces topologically, and we just introduce some conditions on the atlas. So there were a lot of conditions that we had to check, right?
Mhm.
So, but how can we just intuitively know if something is a Riemann surface? For example, you introduce that chair as a Riemann surface. So
I
how
said-
do we know that these conditions hold for a?
No, actually, if you have that theorem that actually part of it was proved by Gauss already, is that any Riemannian surface, if it is oriented, it's a Riemann surface in a unique way.
What is it?
A Riemannian surface is a two-dimensional surface that has a Riemannian metric.
What is it? Riemannian-
Okay, so I just ask me over the break. I'll explain it. So these are. I mean, that you can measure distances here exactly.
I have a question.
Question, yeah.
Higher dimensional.
What's that?
If you have an oriented Riemannian manifold, then is it necessarily complex manifold?
Sorry, say it again.
If you have an oriented Riemannian manifold,
Oriented Riemannian manifold, yeah.
is it necessarily a complex manifold?
No.
No. Everybody only holds
This
for-
is only a two-dimensional phenomenon. Yes,
Okay.
that's right. No. Well, I would love if that would be the case, because that would solve a problem of existence of complex structures on six-dimensional sphere or something. Yeah,
Okay.
that's an open question, but there are many Riemannian metrics on that, but complex structures. Almost complex structures exist, but no, not from Riemannian. I mean, no. I mean, the distance between Riemannian board and complex boards starts to diverge if you go to higher dimensions. It's only a two-dimensional phenomenon.
Even the dimension is not necessarily even, so.
No, but complex structures do not exist in odd dimensions.
Yeah.
That's necessary even dimensional phenomenon. Yeah. No, I mean, two-dimension is very special. It's very special, and a lot of things happens only in two dimensions. In terms of complex geometry. Yeah. Any other questions? Okay, so this is genus 0. Now let's go to one genus up. See what we can do. So if you go to one genus up, so genus 1. Okay, I mean, in the genus 1 case, the theorem or corollary implies that there exists F, or let's maybe put it F, from X. So this guy has genus 1. to C hat with a single pole of order at most 2, right? Pole of order at most 2. But of course, I mean, this by no means would imply that X is isomorphic to or biholomorphic to C hat. And the question of classification of complex structures on genus 1 curves cannot be approached by this theorem. This theorem is not strong enough. So, cannot classify complex structures on G equal to 1 Riemann surfaces this way. So, and I will develop this Abel Jacobi map today and Jacobian of curves, I mean Riemann surfaces that will settle this question in genus 1 case, but that needs more elaborate theory, which we'll develop later today. But there is an example. Okay, so I'm not, but I mean, recall we had an example of this. Of such X and F. Do you remember when we constructed an example of such a Riemann surface of genus 1, topologically, and an F from X to C, such that F had a single pole of order 2? You remember? What was the example?
Can you ask?
Sorry, can you say the question again now?
So the question is this. Give me an example of a Riemann surface of genus 1, concretely, and an F, concretely, which is meromorphic and has a single pole of order 2.
I guess the y is just p function.
That's right, y is just p function. So let me recall this for you. So for X, we took C over lambda. Lambda is a lattice in C. Z omega 1 plus Z omega 2. So it's a lattice in C. So this lattice, right? When you divide X by this lattice, you're identifying these edges and those edges. So the quotient map here takes you into this. And the complex structure, it inherits the complex structure from C. So so this guy becomes a complex, has a complex structure, it becomes a Riemann surface as a result, right? So this is our Riemann surface. Now, what was example F that I constructed? Then I define F of Z to be equal to 1 over Z squared plus sum. This was 1 over Z minus lambda squared minus 1 over lambda squared. Lambda belonging to capital lambda, and lambda is not 0. So you're summing over all lattice points except 0 here. Right? And this is like omega 1, and this is omega 2. Okay, now I should not write f of z. This is a crime. So I just write p of z. It's an insult to Weierstrass to write his function by f. It's p. I don't know if Weierstrass actually used p. Maybe someone else, I think, to use p. But anyhow, so this is p. And I don't know why it's called p, by the way. So, but that's because, anyhow. So this is the function. You can see that we proved that this is actually a doubly periodic function. It's doubly periodic. And what? And it has a unique pole at 0. I mean, at the lattice point. As poles of order 2 at lattice points. These are poles of order 2 at lattice points. So this is as far as the usual complex analysis goes. So they define this map. But then, because of periodicity,
Is the map out of the complex torus or out of the complex plane?
no, originally it's in the complex plane. So this is like a first year complex analysis. You do define this. But then you say, okay, this is because it's doubly periodic, so it goes over as a map over the torus, right? So yeah, here you can say that here goes into here. So again, you get P function. Now this function, because it has poles only at these points, but all these points are identified into one point. Because all the lattice points are identified into one point, and this goes to C hat. I mean the infinity at C hat, right?
But isn't the problem that we haven't included lambda equals 0? Because
Sorry?
we didn't include lambda equals 0.
Yeah.
And lambda equals 0 also identifies with the same term.
Lambda equal to 0, I cannot put lambda equal to 0 here.
Yeah, exactly. And lambda is equal to 0 is identified with that same term.
Here.
No. In the torus, lambda equals 0 is identified.
Yeah. It is the origin, yes.
It's identified with the same point that goes to infinity.
Yes. All these points, if you look at it as a map on C, they go to infinity, but as a map on the torus, there's only one point which that goes to infinity.
So shouldn't we just send lambda equals 0 to infinity?
Lambda equal to 0 goes to infinity? Yeah, it goes to infinity.
Okay.
That's what it. But not okay. So you see, there are 2 points of view you have to have in mind: as a function on C, as a function on the torus. We are interested in as a function on torus. So this gives an example of a concrete example of the map that we constructed in corollary as a beginning of the lecture. So it's an order 2 map that, but of course, I mean, this is like a jewel of complex analysis in the plane. I mean, because it has so many beautiful properties, it's concrete and da. But okay, so that's a recall basically what we did. Okay, so now, I want to, because I need, so I want to derive one more. Do you have any questions, by the way? I want to derive one more corollary of Riemann-Roch. I mean, there are so many corollaries, and I hope we can cover many of them, but I just need one more very soon. So let me write it. So this is new. So this is another corollary of Riemann-Roch. So it's the following. Let X be a compact Riemann surface and P different from Q 2 points on X. So you have this compact Riemann surface of any genus you want, that's okay. And pick 2 points on this. Then there exists a meromorphic differential, one form. With simple poles at P and Q. Simple poles, we are saying at P and Q, and no other poles. And it's holomorphic everywhere else. No other poles. Okay. So this time we are not constructing functions, we are constructing one forms, but you'll see that actually construction of existence of one form is also embedded in Riemann-Roch. It's not just about functions, also about one form. So you'll see why now. So yeah, I mean, this is like any Riemann surface with any genus you want. take 2 points arbitrary, then there exists a meromorphic one form. I said that has simple poles at these 2 points and is holomorphic everywhere else. So how we can prove this? So proof. Let's take a divisor. The divisor D equal to minus P minus Q. Right? So Riemann-Roch says that the following. It says that dimension of L of D minus dimension of L of K minus D is equal to degree of D minus G plus 1. Okay? Okay, now, what is this number? Can you tell me dimension of L of D?
Is it 2?
Why 2?
Degree of D is minus 2.
Degree of D is minus 2, yeah.
And we want things such that f plus the degree of D is greater than or equal to 0.
Yeah.
And so
Should it be 0?
There's an answer. There's another one which is 0. So who is right? Yeah.
so f has a simple pole of P and Q.
We want to construct it.
Right. It's the dimension of the space of things that has simple poles of P and Q. And
No,
No.
don't work. Any other answers? So why is it 0?
Because it's negative 2.
Exactly. It's a negative degree divisor. So this is 0 since, you see, I proved when I introduced L of D, this language, this terminology, that was the first thing I proved, that if D is a divisor of negative degree, then L of D is actually 0, and its dimension is 0 as a result. So this is a 0-dimensional vector space, so its dimension is 0. Since degree of D equal to negative 2 is less than 0. So this evaporates. This guy is negative 2. So then I get that minus dimension of L of K minus D is equal to negative G, negative 1. In other words, we derive that dimension of L of K minus D, right, is equal to G plus 1. So, but now let's see what this entails. This just tells me this is really dimension of a space of all meromorphic one forms. All meromorphic functions on X, such that divisor of F plus K. K is a canonical divisor, right? Minus D and minus D. What is minus D? D is minus P minus Q. So this is plus P plus Q is bigger than or equal to 0, right? So we discovered that dimension of such spaces is at least is exactly equal to G plus 1. Because look, this is a definition of K minus D here. L of K minus D, its definition is this one, right? So that's what you. Okay, now let's see what we can say. Well, this D, I can, now here is always, I said that the Riemann-Roch also tells you information about meromorphic one forms in the following way. Because this K, you can always write it as divisor of some omega. And then divisor of F plus divisor of omega is divisor of F omega, and then now you have a one form, okay? So let's say this now. So this is equal to dimension of in the set of all F such that divisor of F omega, right, plus P. So I just write it bigger than or equal to negative P, negative Q. So this is basically any holomorphic, meromorphic one form, right? So it's a meromorphic one form. And in fact, any meromorphic one form can be written as f omega once you fix omega, because you can divide two by each other, and then you get a meromorphic function in front, and that's what it is. It's always, this division is always very helpful. Okay, so this dimension is equal to G plus 1. Okay, so now I can write this statement in the following way, because as I said, there is a correspondence between meromorphic functions f and meromorphic one forms f omega. So I can just say that this is the same thing as so now I'm going to change notation a little bit. So instead of all omega belonging to omega 1 of x. Now this omega is not that omega. I mean, this is very general omega now. Omega of x, this is a meromorphic one form. I mean, this is the space of meromorphic one forms. Such that divisor of omega is bigger than or equal to minus p minus q. I mean, this dimension is equal to G plus 1. Okay? Now, there is a G-dimensional subspace in this space. So now there exists, so let omega of x equal to a space of holomorphic one forms, not just meromorphic, holomorphic one, space of holomorphic one forms. Globally defined holomorphic one forms, right? On x. What is the dimension of omega of x? It's G. This is something that I said I won't prove it, but this is also I used it during the Riemann-Roch theorem. It can be proved using different methods, but I did not prove that. But this dimension is G exactly. So the dimension of omega of x is G. But this omega of x is inside this space. Okay? Is inside the set of all omega belonging to meromorphic one form such that divisor of omega is bigger than or equal to minus p minus q, right? Why this is the case, by the way? Why holomorphic one forms is inside this space of meromorphic one forms? Because a holomorphic one form, by definition, is a one form whose divisor is bigger than or equal to 0. If it is bigger than or equal to 0, it's bigger than or equal to minus p minus q as well. So that's automatic. Okay, so this is automatic. Okay, so this space is G plus 1 dimensional. There is a subspace G dimensional. So there exists one element which is not here. So there exists one meromorphic one form which is not holomorphic and satisfies this condition.
What if it has a simple p but not?
Huh?
What if it has a simple for p but not q?
Say it again.
What if it has a simple for p but not q?
Yeah, but that cannot be exactly. Yes, I will ask you. Okay. Now let me write it. So far we proved that there exists omega, which belongs to okay, I don't know, this is space right hand side, but not in omega of x. So, I mean, there exists omega, a meromorphic, but not holomorphic. I mean, meromorphic, but not holomorphic. With a divisor of omega bigger than or equal to minus p minus q. Now the question is why we cannot have, in fact, that's a possibility we have to reject. Why we cannot have a meromorphic one form that has a pole only at one point. Okay. I give 50 cents to anyone. I don't want to denigrate this question, but that's my wealth in my pocket today. Okay, $1.
It has something to do with residue.
Yes, exactly.
Some of
So you get 75 cents because it was between the two.
the residue should be zero.
Exactly, the residue should be zero. So you cannot have something that has a pole only at one point because the residue is going to be non-zero. So it must have two poles, and then the residue will be inverse of it, I mean negative of each other, and they cancel out. Okay. So the residue theorem shows indeed, exactly, thank you. Residue theorem implies that omega must have simple poles at both P and Q with negative residues. So this is what we wanted anyhow. So this is kind of more typical application of Riemann-Roch. You have to choose the divisor in the right way. We just choose this divisor. I mean, you could choose any other divisor, but it doesn't lead to the result. Only this divisor more or less leads to the result. So this is the part of the task. You have to choose the divisor in the right way and argue and then count dimensions, and then you'll find either meromorphic functions or meromorphic one forms, both that solve your problem. So this is okay. Any questions? You want your 75 cents? You're not going to get rich. Okay, so now we can move to, before we take a break, we can now move to the next thing, which is actually is related to this issue. So that's, so now I'm going to define Jacobian of a Riemann surface. Riemann surface. Oval Jacobi map. And Oval's theorem. So the three topics. Okay. So again, our standing assumption is that X is a compact Riemann surface. Riemann surface. And so let's recall our notation. Omega of X is the space of holomorphic one forms on X. Of course, as we discussed many times, I'm using the fact that dimension of omega of X over C is G. So it's a complex vector space, like everything we do is over C. And in fact, it's also a real vector space. Maybe you should have this picture in mind. It's also a real vector space. So its dimension as a real vector space is 2G. It's like a 2G dimensional real vector space, like double dimension. So I want to define something called period pairing. So it works like this. So we define a map from H1 of basically X plus omega of X to C. Or we can see this alternatively as, or equivalently as a map from H1 of X going into omega of X dual. Okay, so if you define a bilinear map into this, it's the same thing as you're defining a linear map from this one into. So everything is defined. I mean, this is the complex dual of omega of X. I mean, this is the HOM of C of omega X and C, right? This is a linear complex dual of omega X. Now, what is H1 of X? I mean, I should write really H1 of X and Z. Z. So this is the integral singular homology. Integral. I mean, so let me put it this way: singular homology with integral coefficients. With coefficients in Z. Okay. So if you haven't seen this before, that's okay. I just define it now. So let me define this, and then so how is it defined? Okay, so to define this, okay, I'll just erase this first part. So I define this singular chains C0 of X, C1 of X, C2 of X. So Ci of X is the free abelian group. Okay, so let me put it this way. Yeah, is the free abelian group generated by I chains, maybe. I mean, I'm not sure okay, so what is the right word for this? I'm a bit hesitant to use chain, but let me put it this way: I chains in X. So let me put it this way: zero chain in X is just a point in X. It's just a point in X. Or you can say is a map like, I don't know, C from point 0 to X, right? So C0 of X, which is the free abelian group of zero chains, is our old friend. What is it? You just take these points and you form the free abelian group of those points. What is that? This is our divisor. This is our old friend divisors, right? So this is exactly, so C0 of X is just divisors. Is dx. Exactly. Now, what is C1? I mean, yeah, so C1 is generated by curves in things. Okay, so is a set of such linear combinations. So Ni, Ci. So this Ci from interval 0, 1 to X is a smooth map. Now, when you learn algebraic topology, they tell you these are continuous maps because you want to work over any topological space. So you're forced to take only continuous maps. But if you are over a smooth manifold, if you restrict to smooth maps, the two theories are the same. You can show that either continuous or smooth, they give you the same result. So because I want to, okay, so let me put it this way. This was a smooth, actually. This was a smooth maps. Okay, so now what is this guy? So basically you just take bunch of you just take this map like connecting this point P to this point Q, and there are these possible holes. So you just take all possible curves here and then you take linear combination of these curves that are embedded in your surface. Right? So if I derive some of this, it's going to start look like on these pictures. If you know that artist, I don't know. Anyhow, so this is C1 of x, and what is C2 of x? Exactly similar like this is a free abelian group, but in this case it's generated by maps from not interval but triangle. So it's a map from triangle. Okay, so there is this notation. I don't know. So this guy. I mean, this is a simplicial. I don't know, simplicial set or something like that. So this is the set of all x and y belonging to R, such that x plus y is less than equal to 1, x is bigger than equal to 0, y is bigger than equal to 0. So these are two simplices, if you want. I mean, it's a two simplex. So as I go on in the lecture, I remember the terminology. So I just get better. As we go on, I get better and better with the terminology. Now I know what should I have said here. These are the simplices actually inside this, and this is the standard two simplex. This is the standard one simplex, and the point is a standard zero simplex. So that's so that's the way you define singular homology. So the spaces are defined. So okay, I mean for this one you just take strange objects like this here, and then take integral linear combinations of those, right? Now the question is what are the maps here? So I just have delta, differential delta, right? So what are the maps? Before we just take a break, so let me define map. You have seen it most probably, so but I just define that's okay. So D of C, I mean D so from C1 of x to C0 of x. So D is uniquely defined, uniquely induced by its values on one simplices. So in other words, D of C is equal to C of 1 minus C of, okay, so why not? 1 minus C of 0. So there is this C, which is from 0, 1 to x, right? It takes your interval into your surface and just puts it into some curve here. And then you just take P and Q. Now the question is, do I need C of 1 minus C of 0 or C of 0 minus C of 1? Which one should I choose?
I think it's usually C of 1 minus C of 0.
C of 1 minus C of 0? You think it should be?
Yeah, I mean, that's I think what's usually taken.
Yeah, because C of 1 is from.
C of 1 is just N minus.
Yeah.
But I can never convince myself which one to choose. I think this is a sign of that there's no justice and there's no reason in the world. It's just completely arbitrary and it really bothers me. But okay, so anyhow, so you just say, okay, since you said I just take C of 1 minus C of 0. Okay, so now what about, okay, so then, yeah, cool. Okay, now what about D from C2x to C1x? What do you do in this case? You just restrict your C to these things. So you just take it here and then subtract here and then add here, because these are kind of intervals, all of them, right? Okay, so I have to take a break now, but so you can check that D composed with D is equal to 0. This is not difficult. And then we define H1 of X and Z to be exactly kernel of D, like in any homology divided by image of D. So kernel of D are called one cycles. These are boundaries of things. So these are things that bound actually. So you see, if you have a boundary of this, it's like a boundary. This is a one cycle. And okay, this is H1. And I don't care about H2. H2 is just kernel of D, but that's okay. Don't care about H2. And if you care about H0, so what is H0 of XZ? This is by definition just C0 of X divided by image of D. Can you tell me what is that? What is this space?
So it's the divisors mod,
You're dividing exactly all divisors by these images.
which are,
Huh?
and I'm just trying to figure out what the quotient imply.
Yeah. What is the quotient?
Co-sensitive.
Huh? I mean, okay, so we are in a special case that X is a connected Riemann surface. Well, our Riemann surfaces are always connected. But I mean, the question exists also for general topological space. If you take a general topological space, X, you can define it, so that's not a problem.
It's just the path components.
Exactly, it's the space of past components. And this is exactly goes into the kernel of this augmentation ideal. So augmentation map. So this is that's a straightforward to prove actually. So this is isomorphic to Z. I mean, is the free abelian group on connected components. So it is a group and an abelian group. So in this case, Z. Okay, so I think we take a break. I come back, then I will define this period pairing, and then I will just define